So building regression models means I have some data. How do I then from there find the best model? First of all, we can look at scatter plots of the data, and that will indicate to us some ideal relationships, whether it's linear or nonlinear. And if it's nonlinear, we can transform the variables accordingly, as we saw earlier with those plots of the usual simple functions. I just fit all the variables, of course, and remove the least significant, repeat this, and reintroduce the non-significant terms one at a time to confirm that they don't belong in the model. So how does this work? The most important aspect, as I said before, is residuals. They contain information on the missing components of the model. So what we'll do is we'll plot residuals against fitted values, and they will reveal to us what else is required. Now, packages will have some stepwise backward forward regression models. R has them as well. They're a good guide, but they must always be evaluated against the model you fit by hand as well. Model selection manually also gives you structure of how the data behaves that you understand if you look at the step-by-step fitting of the model. Example over here is some data. Y against X. There's certainly some curvature over here. Exactly how, we don't know yet. What do we try? Simple. Start with the simplest model. Just straight line. And then examine residuals against fitted values to see what else is left. So for this model over here, we fit the simple linear regression. The model equation is y equals 59.6 plus 12.9x. But the residuals against fitted values looks like this, and that indicates a squared term. So I require here in the model an x squared term. So I add that in there. Here's my output for x and x squared. I put in x and x squared in the model. They're all significant. If I look at the residuals against fitted values this time, I get something else here. Now, this is a square root, if you remember before, square root. So it's doubled up here because of the negativity as well, but this half here at least is a square root function. So I require to put in here a square root of x. So far the model equation is 11.7 plus 27.x, 2.7x plus 0.25x squared. If I now include a square root term as well, where x square root of x and x squared, they're all significant, I've got a very low standard error, tiny, and the R is 1 now. So this looks like a very good model, but I will not now. Let's look at the residual plot. Now if you look at the residual plots here, there may seem to be some pattern here, but really look at the values. They're really tiny. In other words, the pattern I'm seeing is not there at all because the residual is actually very small. And this is now my model equation. So I've got from some data that certainly didn't look linear, but I've actually found an equation that fits the data by this step-by-step idea. Fit a simple model, look at the residuals, find the next component, look at the residuals, find the next component, until you get nothing left in the residuals. In fact, here is the thing on the scale, residual plot, very tiny as you can see. Data itself was in the order of tens. If you look at the data itself, the value of the data, the first plot we had a look at, you see the data is in hundreds over here. And residuals in the 10 to the minus 13, 14 is tiny in this case. So what we've done here, and so if you look at the plot of the actual fitted values against the observed values, they're straight line, exactly the straight line. They match up exactly. Exact fit almost. So if we look at diagnostics, normal probability plot, no rest of it looks okay. This is the normal probability plot. It doesn't look very different from straight. Histogram looks reasonable. What about looking at residuals? We've seen that already. Now, this is exactly the equation used to generate the data in the first place. So I've got my values of x, and I perform this kind of transformation on them to find my y. But you see, by using regression model building ideas of fitting a simple model and extending that by looking at residuals, I have come back to the exact equation that I had started off with. So the regression analysis of fitting of this building of models is a very powerful idea. What we did here was we fitted some nonlinear model here by simply transforming the variables. And the typical ones we'll be using is things like roots, square root, cube root, whatever, log exponential, and so on. Sometimes, instead of transforming the x variables, it's easier to transform the response variable. So let's have a look. Next idea is solve 5 looked at only continuous variables for x's and y's. What about including categorical variables as well? Well, that's the